Right, we've got a
That big red button would go live at night.
The one that says, "Do not press this red button unless you want to go live."
I've just got a screen telling me how to learn the guitar fretboard and who really killed Brian Jones.
Oh, right.
So nothing to do with the LES.
not to do. Well, Brian Jones does the Sky Night books as well, doesn't he? Hey, there we go, Mark. Well
Brian
done.
Jones was one of the guitarists from the Rolling Stones.
Rolling Stones. Well, original Rolling Stones.
Or Stolen Roses, I was going to say.
Stolen Rose.
Right,
Okay,
we are
we're on.
live streaming to YouTube, and I think we should start the meeting at 1909. Right. Okay. If I could ask everybody to mute your mics, you can leave your cameras running. It gives good feedback for the lecturer if they can see your face. But if you make sure you're all muted, so we don't hear you all drinking tea and things like that. And I would like to welcome you to the October 2021 meeting of Liverpool Astronomical Society. We're online again, as you can see. And the first item on the agenda is apologies for absence. And I've got apologies from Gabrielle Archer, Matthew Card, David Crabb, Jared Gilligan, Brendan Martin, and Steve Southern. There may be a few others that have come through by email. In the meantime, they'll be added to the minutes record later on. Okay, now item 2 is the minutes of the previous monthly meeting, which was, as you may remember, last month on the 17th of September. They've been taken as read and they're available on request. If anyone wants a copy, just send me an email. I'll send them out to you. Okay, the acceptance of the minutes, I can't actually accept them myself. The council has to do that, so that's over to that. New members is item number 4. We can't do that at the moment. Hopefully we will be doing soon. So we'll move on to number 5, which is announcements. Now we've got 2 announcements from myself, from council. The first one, most important thing, we've got a council meeting coming up this Thursday, the 21st of October. And the main topic of that meeting is going to be about reopening. And we would like to, if any of the members would like to join us at that meeting to give input on what we want to talk about is how can we do it safely? What sort of restrictions will we need to put in place? What are you as members comfortable with doing? Should we enforce mask wearing? Should we enforce hand sanitizer? All these kinds of things. So if anybody would like to join that meeting, that's on Thursday, the 21st of October, and I'll send an email out to you as well with details for that. The second announcement from myself is just a reminder, don't forget the clocks go back on the 31st of October at 2 AM and we go back into winter time, into ordinary time. Does anybody else have any announcements that they'd like to make? No? Okie doke. Right then, with no further ado, I shall introduce the speaker. We have with us tonight Mr. Andy Briggs. He's joining us all the way from Spain via the wonders of the internet. Andy is an astronomy writer and broadcaster. He writes for magazines and websites, and he's also a presenter on the popular Astro radio station, which goes out to over 250,000 people for each show. Some of you may have heard it. You may be familiar with Pete Williams. He is one of the other presenters. He runs it, but Andy is also a presenter on there. And his title for his lecture is How to Photograph a Black Hole. And you might be thinking we've had talk about that already. We did, from Professor Derek Ward-Thompson from the University of Central Lancaster. Now, Derek's talk was more from the academia side of things. Andy is going to explain from his side, and I hope it'll give a different perspective on the same topic to flush it out, to give you a better idea of it all. So I will turn over to Andy, and there we go, Andy.
Thank you very much, Mark. Oh, good evening, everybody. I hope you're all well and safe during this terrible pandemic. And as Mark said, I'm going to talk to you today about how to photograph a black hole, brackets again. So as Mark said, I've probably got a new perspective on it that perhaps isn't at such a technical level as the talk you previously had. So just give me a second to sort my end out. So let's just get this up. Just give me 1 second. And let's see where we go with this. Okay, I'm going to show this. Hang on, let's get PowerPoint running. One second. Okay, just give me a second. I've got something gone wrong here. Right. Need to restart that. Okay. Let's just show this slide. Okay, so I don't know whether you can hear anything. Can you see my screen now?
That looks great. Yep.
Okay, let me just get the sound. There should be some sound now. Is there sound? Anybody hear anything?
Yeah, that's great.
Sounded good,
Okay,
Andy.
that's great. All right, that's great. Right, so if you're all sitting comfortably, then I'll begin. So, how to photograph a black hole. This black hole in question, of course, is the black hole in the middle of the M87 galaxy. Now, before we actually get onto the black hole itself, I'd just like to go through a few things. Firstly, why would we try and acquire an image of a black hole in the first place? What's the point of it? So first thing to say is to prove that black holes actually exist, because before that iconic image, and that image, which I'm sure you're familiar with, is destined to go down in the history books of humanity's first direct image of a black hole. And even before this image was taken or acquired, there were many people who were still saying that black holes don't exist, it's all a load of nonsense. And there are still people on Facebook saying it, even after this image. And the number of people who've said that, and I've just quietly posted the image and they've come back and said, well, that's fake. So you can't win. Anyway, it was indeed to prove that black holes actually exist, which was a pretty important thing to do. All evidence pointing to the existence of black holes before then was circumstantial. We knew that there were supermassive objects in the dark that we couldn't see, that were having gravitational effects on other bodies, that were emitting enormous quantities of radiation, but whether they were black holes or not had not been proven. And I think fairly conclusively it now has. Black holes are the most extreme objects in the universe. If you want to study the laws of physics, you need to test them until they break. And a black hole is the place where they do. So thanks to Einstein's relativity, we had a good idea about how gravity, light, and matter behave and how they interact. Now, with this image, we could directly test those theories, and they have been tested. And believe it or not, and this will come as no surprise, Einstein has come out with flying colors. The behavior of this black hole in M87 matches exactly what was predicted by relativity in many ways. So this was a fantastic step forward. Black holes have an incredible effect on their surroundings. the existence and evolution of galaxies, stars, and perhaps even life itself depends directly on black holes. And this is only something that's been really considered in the last decade or so, the incredible influence that black holes have on their host galaxies and the stars and the planets and perhaps even life within them. And just to demonstrate the incredible effects that black holes can have on their surroundings, here's a picture of an optical picture of the galaxy Hercules A. Now, you know, as a galaxy, it doesn't look anything really special, looks a little unusual, but there's nothing incredibly strange about it. But when I add in a radio image of the same galaxy, we can see that either side of Hercules A, there are these enormous jets being shot out from the center of the galaxy, which pile up in these huge lobes of material. And this is only visible in radio light. Now, the size of this is absolutely unbelievable because the span of those jets is 5 million light years. So something in the middle of the Hercules A galaxy has enough energy to focus those jets and create those enormous lobes of material where the material ejected from the center of the galaxy meets the interstellar or starts to pile up against the interstellar medium across 5 million light years. So you can imagine the energy required to do that. Actually, you can't because it's just incomprehensible, as I'm going to demonstrate to you a little later. Now, the energy actually required to power those jets to do what you're seeing on the screen is the equivalent of about 3 billion supernovae. That's how much energy is being pushed into those jets, squirted into those jets, which is, you know, as I said, an incomprehensible amount of energy. Let's talk a little bit then about the galaxy that the black hole is in, M87. And here's just a size comparison. On the left, we've got the pretty wimpy Milky Way. And next to that, Andromeda. This graphic's a little bit out of date because I think now we've discovered that Milky Way and Andromeda are about the same size. We used to think Andromeda was about a third bigger, but apparently the latest data indicates that Milky Way and M31 are about the same size. Then we have M87, and then on the right, just for comparison, we have the largest galaxy known, which is IC 1101. And if you compare that to the size of the Milky Way, you can see how massive that galaxy is. Nobody knows as yet exactly how it got that big, but obviously it's the result of at least one galactic merger. So that's quite an interesting galaxy on its own. And M87 in the middle. So the M87 galaxy is a lot larger than the Milky Way. Again, it's the result of galactic mergers, and it's an elliptical galaxy, as I'm sure you know. Zooming in on that galaxy, this jet of material, which squirts out of the middle of the galaxy, was first noticed in 1918 by a British astronomer, and he didn't know quite what to make of it. And in fact, nobody's known what to make of it until the last couple of decades, when somebody suggested it could be the result of a black hole. Now, there are actually two jets coming out of M87. This one and the other one is pointing almost directly away from us. So it's actually not that visible. It's actually lost in the glare from the middle of the galaxy. And the span of this jet is absolutely unbelievable. So the first thing to say is it's 5,000 light years long. This jet is 5,000 light years long, or I worked it out at 29,400 trillion miles. No idea what it is in kilometers, I'm afraid, because I don't use those. So it's 29,400 trillion miles. And the opposing jet going the other direction, I've just drawn a yellow line, roughly the direction it goes in, because the visible jet is pointing more or less directly at us. Therefore, the other one is pointing more or less directly away from us. So that's not that visible. Let's zoom in on M87 now. And I'd like to do this to show you how absolutely tiny the M87 black hole is compared to the size of the galaxy. So I'm going to take you on a tour into the heart of M87. You're going to see various images in X-ray, optical, and radio light. If you look at the bottom left of the screen, it'll tell you which one you're looking at. and where it comes from. So join me as we just go on a brief flight into the galaxy M87. And so we arrive finally at the black hole. And as you can see, compared to the size of the galaxy, it is absolutely tiny. But with our human scale of things, it is absolutely gigantic, of course. Now, can I ask you, did that video perform? Was it smooth, that video? Was it a bit jerky?
It was a little jerky, but it wasn't too bad.
It conveys the message, doesn't it? It was stepped through.
Right.
But conveys the message.
I've got a couple of videos. What I might ask you to do, actually turn your cameras off so that we've got the bandwidth so that the videos are a bit smoother. Is that all right with everybody?
That sounds good.
Yeah.
No problem.
If I could just ask you to turn your cameras off. That'd be great. That gives us a bit more bandwidth for the videos. Thank you so much. So there we are. So that was a trip to the heart of M87. Now, this is the famous image, of course, acquired by the Event Horizon Telescope. And I'd just like to point out a few things about this image. Firstly, the jets that we saw very clearly in visible light, but at the wavelength of light that the Event Horizon Telescope was receiving, which is millimeter and sub-millimeter wavelengths, those jets are not that visible. So you can just see them as indicated by the arrows, the two jets. Now, this phenomenon is called Doppler beaming. You can see that the bottom half of the jet, there are patches where it's brighter. And this Doppler beaming was something predicted by Einstein. And Einstein said that material moving towards us should be brighter than material moving away from us. And he was demonstrated absolutely correct with this image, because the disk is tilted slightly so that the bottom half of the disk is moving towards us and the top half is moving away from us. But this was another verification of what Einstein predicted. This Doppler beaming, where material moving towards us is brighter than material moving away from us because it acquires more energy. Let's actually have a zoom into that black hole, and we'll first of all say that what you're looking at is not a photograph. I know the talk is called How to Photograph a Black Hole, but that is a misnomer, because I wanted to point out to you that the media was saying this is a photograph of a black hole. It's not. This is a map of radio waves, because the Event Horizon Telescope looked at the black hole in radio wavelengths, millimeter and sub-millimeter radio wavelengths. So it's not a photograph. It's not what you would see if you were there. It's a map of the relative brightness of radio waves. Now, as you know, radio waves don't have a color because we can't see them with our eyes. So when the team had to decide what color to make this image to map the radio waves, they decided on this sort of orange-yellow color scheme. They went through a load. They went through blue. Luckily, they didn't go through pink, but they went through quite a few colors to map the radio waves, and they decided that this gave the best image with the most information. So this is not the real color of the material around the black hole. It's not a photograph. Let's zoom in. You're now going right into the maw of the black hole, if you like. And the next thing to say that this is not the event horizon. I know it's called the Event Horizon Telescope. The media were reporting that it's the event horizon of the black hole. It's not. This black area is known as the black hole shadow. What does that mean? We're going to come to that in a little while. I'll explain exactly what you're looking at there. The black hole itself is somewhere in there. I've put this black circle in there just to demonstrate that it's in there somewhere. It's probably a bit big to scale, but it's in there somewhere. And of course, we can't see it because it's black, but the actual black hole is within that black hole shadow. Let's zoom in and give you some facts and figures about it. Now, the M87 black hole is designated M87 asterisk. The asterisk means a black hole, in the same way that the supermassive black hole at the center of our own galaxy is designated Sagittarius A asterisk or A star to designate a black hole. So this is M87 asterisk. It's 54 million light years away. It's 318 million trillion miles away, if you want to look at it in miles. Its mass is about 6.5 billion times that of our sun. So it's a heavyweight, but not the heaviest black hole by any means, because the black hole that has the most mass that we know of so far is a quasar called TON 618, and that has 66 billion times the mass of our sun. So that is almost exactly 10 times more massive than the M87 black hole. The black hole consumes about 90 Earth masses of material per day. So that material around the black hole is going into the black hole at the rate of 90 Earth masses per day. And yes, I did work out how much that is, and that is that many tons. So the black hole is swallowing that many tons of material every single day. And as you can imagine, that is a hell of a lot. We're talking, gargantuan things with this black hole, things off the scale, things that our poor simian brains can't really comprehend. It's rotating at about 90% of the speed of light, and the disk of material is rotating at about 1,000 kilometers a second. So that's the speed of the rotating disk of material around it, spiraling into the black hole like water down a plug hole. The size of it, of the black hole shadow, the whole structure, is this size. As you can see, there's the sun, there's Pluto, there's the distance of Voyager 1 from the sun, and as you can see, the black hole shadow extends to about that distance all around the black hole. So this is a truly massive structure that we're looking at. And now I'd like to talk to you about bicycles, because this photograph, as I'm sure you know, is a bicycle dynamo. And how does this work? Well, what it does, it takes the rotational or kinetic energy of the bicycle wheel and converts it to electricity. Why am I mentioning this? Because I want to talk to you about the amount of energy that is present at that black hole and where it comes from. So we're going to explain this with the aid of a bicycle dynamo. Now, the idea behind this is when we look at the dynamo, what if we had a massive dynamo, a huge dynamo, and we put it against the black hole? And the black hole, as we know, is spinning at 90% of the speed of light, far faster than any bicycle wheel. And how much energy would that dynamo be drawing from the black hole if we had a giant dynamo? And let's investigate this. To do this, I would like to introduce you to a new unit of measurement, which you may not have come across before. And this is a FOE, F-O-E. One FOE is the energy released in a typical type 2 supernova explosion. All type 2 supernova explosions emit roughly the same amount of energy, and that's 1 FOE. And that is equal to 10 to the power of 51 ergs. You see where FOE comes from, F-O-E, 51 ergs. 10 to the power of 51 ergs, or that many ergs. That's 10 with 51 zeros after it. Now, you may say, how much then is 1 erg? An erg is a bit of an old unit of measurement now of energy. It's not an SI unit, but it was used a lot, certainly when I was young, which was, only a few years ago. And I'd like to demonstrate how much is 1 erg so that you get an idea of the energy involved. Now, 1 erg is approximately the amount of energy consumed by a housefly doing a push-up. I kid you not, that is 1 erg, the amount of energy consumed by a housefly doing a push-up. And I'd love to be able to say that I have a video of a fly doing a push-up, but no, I have actually. And here we are. Now you see, wait for the fly, wait for it. There, that movement of its front legs, when it pushes itself up, that's a housefly doing a push-up. And that is 1 erg of energy. And I just love the fact that somebody made a video to demonstrate this, which is absolutely marvelous. So that's 1 erg of energy. And 1 pho is therefore 10 to the power of 51 of those. The term pho was invented by Jerry Brown and Hans Bethe because they kept finding the number 10 to the power of 51 in lots of astronomical things. And I'm not sure what anybody's ever really explained why, but it seems to come up a lot, 10 to the power of 51 ergs. And if we manage to put our dynamo against the black hole, it's an amazing amount of energy. The sun, for example, will release 1.2 pho during its lifetime. So during its whole, 10 billion years history, the sun will emit just a little bit more energy than a typical type 2 supernova. If we did that with our black hole, if we put the dynamo against it, the rotational or kinetic energy of the M87 black hole is 10 trillion pho. So in other words, that black hole is emitting 10 trillion times roughly the energy that our star will emit in its whole 10 billion year lifetime. Now, I said earlier, where does this amount of energy to power those enormous jets come from? And now you know why, because the kinetic energy of this black hole is absolutely amazing. And that energy is used to generate those jets across all those 5,000 light years of space, or 10,000 if you include both of them. So that's the amount of energy that we can get out of a black hole with a huge dynamo, 10 trillion times the amount that our sun will emit during its whole lifetime. Unbelievable. And I'd like to talk to you now about that business of the black hole shadow. Now, here we have a black hole and it has some photons passing by it. And their path is curved around the black hole so that all the photons end up following parallel paths. Let's just run this. So you can see the photons have their paths bent and they all end up following parallel paths. So if we look at this from the Earth, what we actually see is this. The black hole in the middle, which of course is invisible from the Earth, but we end up seeing this big black area where there are no photons. And that is called the black hole shadow, because all of the photons have their trajectories bent, so they're all parallel, and there's nothing in the middle, if you like. Now, when scientists looked into this black area, they found something truly amazing. Sorry, couldn't resist that. Anyway, let's look at this in a bit more detail, because it's a slightly more complicated idea. So first of all, let's look at the simple photons that have their trajectory altered just a bit by the black hole. Of course, it's important to say that the photons themselves don't have their trajectories altered. It's space-time itself that is curved, because light can only ever travel in space lines, so photons aren't deflected. So the space itself is bent. Now let's look at the case, first of all, as before, of the photons that pass a little bit away from the black hole and have their trajectories actually changed just a little bit. And if we put a few more of those in, actually, the type of ring that forms as seen from the Earth looks more like a sort of a spiral. And then we have photons that loop once or maybe twice around the black hole. And if we put loads more of those in, their paths are more complicated and they form that type of a ring. Photons that, have really strange paths around the black hole, complex paths around the black hole, before they are ending up being fired or shot towards us, end up creating that type of a ring. And if we put all of those together, all of those photons passing at different distances from the black hole, being deflected by various angles, this is what we should see from the Earth. Now, this is new. This was only worked out, I think, less than 2 years ago, that it's not a simple case of a simple ring around the black hole. We've got multiple rings of different types. I hope that's fairly clear. Why is this important? Because this is a history of the photons that have passed close to the black hole. So by examining these different rings, we can find out a lot about the behavior of gravity in the vicinity of the black hole, exactly how it warps space and deflects those photons. But you may ask, well, hang on a minute, why doesn't the M87 image look like that? Because the M87 image actually looks like that, and looks like that. It looks like a donut. But this is what the Event Horizon Telescope saw. Why was that? Simply because the Event Horizon Telescope did not have sufficient resolution to pick out those individual photon rings. They all blurred together. I mean, come on, it was the first attempt and it wasn't bad. But in the future, with the Event Horizon Telescope improving, we should be able to see those individual photon rings and learn a lot about the behavior of gravity in the vicinity of the black hole. So I hope that's fairly clear. So here we have the Earth, and with the black hole in the background, not to scale, of course, but I just want to tell you what sort of an achievement it actually was to acquire that image. The capturing of the image of 87 asterisk was like seeing something the size of an atom at arm's length. So this was the technical achievement, to take something the size of an atom, imagine holding it at arm's length, and that was the achievement, seeing something that small. Another way of putting it is that it was like reading the writing on a coin in New York from London. So this isn't just seeing a coin in New York from London, this is actually reading the writing on it. So this was another way of expressing the same thing. It was an incredible technical achievement. So what is exactly the Event Horizon Telescope? Well, it's an international project that was developed over more than 10 years, involving 300 scientists and engineers, or more than 300, from around 20 scientific institutions worldwide, with the single ambition of imaging a black hole, preferably the event horizon of a black hole, but that's not there yet. We may be able to do that within the next few years, we'll see. Its goal is to image the event horizon of a black hole. It's a global array of radio telescopes, which I'm sure you know, linked together using very long baseline interferometry. That's the technique used, or VLBI, and I'll talk about that in a little while. Data from all of the telescopes are combined to create an array the size of the Earth. Now, one single telescope would not have the resolution to see something which on a cosmic scale is tiny in the center of M87. So the VLBI technique allows astronomers to combine the data from all telescopes and end up creating an array, the size of the Earth. And here is the Event Horizon Telescope. It's a global network of radio telescopes. As you can see, they're in all sorts of locations. The most northern is the Greenland Telescope. Then we've got them in Hawaii. We've got the famous South Pole Telescope, and regular listeners of Astro Radio know that we have the scientists at the Antarctic Research Station as regular listeners to Astro Radio, and they quite often mail us during a program. And we've got them in Europe, in France, in Spain, and there are the locations. Now, the ones I've marked with a vertical yellow line are the telescopes that actually took part in the observations in 2017, which acquired the image of the black hole. The others have come online after that and are being used in this year's observing run, which I believe is underway at the moment. So the two mentioned there are the Kitt Peak at the bottom and the Alma Observatory. That's the new Kitt Peak addition to the array of the Event Horizon Telescope. And then this is the one in France. And looking at the photo, I always say that looks a lovely mountainous area of France. I wouldn't mind visiting that one day. So these are new to the Event Horizon Telescope. And the more telescopes you have, the higher the resolution. It's as simple as that. More telescopes, higher resolution. We mustn't also forget the two processing centers where the data from the M87 image was processed. And one is at the MIT Haystack Observatory in Massachusetts, and the other one is the Max Planck Institute for Radio Astronomy in Bonn in Germany. And these were the two places that ended up processing the huge amount of data that was acquired in capturing the image of the black hole. And also a very important addition to the array was the Alma Observatory up in the high plains of Chile. The Atacama large millimeter submillimeter array. This has such exquisite resolution. As you may know, it's an array of 66 radio dishes, and under the clearest, most stable skies in the world. The fact that it's clear is not important to radio astronomy, of course, but stable air helps. And without adding in the Alma array, the image couldn't have been taken because it had the necessary resolution to acquire the image and give the other telescopes a bit of a push, if you like. And in fact, Alma has become the whole hub of the array thanks to its incredible sensitivity and resolution. So at each site in the Event Horizon Telescope, we got a radio telescope dish that looks a bit like this. And I'd like to now introduce you to the Event Horizon telescopes one by one. So here's a short video to introduce the telescopes to you. So for the next 4 minutes, I'll sit back and go on a tour of the Event Horizon telescope. Okay, so that was a tour of the telescopes in the Event Horizon telescope. So I hope you enjoyed that. As you can see, quite varied looking telescopes in lots of different locations all over the world, a true international effort. I'd like to talk to you now about the technique that they were using called very line baseline interferometry. And we have two British astronomers to thank for this. The famous astronomer Sir Martin Ryle, who won the Nobel Prize in 1974 for his work on radio astronomy. And his work was finished off, if you like, and refined by Roger Clifton Jennison. So these two gentlemen really, between them, invented the technique of VLBI. Let's ask the question, the obvious question, why do we need to use VLBI with EHT? Because one single telescope would never be able to resolve it, as I said. You need a combined array to give us a telescope the size of the Earth. And VLBI is this technique that allows the creation of this virtual array, if you like. So let's have a look at this. Let's take a simple example. We have two radio telescopes looking at a target, in this case, a black hole. And if we link those two telescopes, we can actually create a virtual radio dish, which is the size of the distance between the telescopes. So this is a very simple example of VLBI, using the combined power of two telescopes to create a single virtual telescope. Now, you'll be probably pleased to hear I don't intend to go into the science of exactly how that's done. A, because it's incredibly mathematical and complicated, and B, because I don't understand a word of it. So we'll just leave it at that to say there is a way of linking the telescopes so that they can function as one big telescope. And if we think of this in terms of the Earth, they're our two telescopes, they're linked together, and they form a dish that size, a virtual dish that size. And we can add in other pairs of telescopes that are linked over the surface of the Earth so that we end up with lots of different virtual dishes, different sizes because of the differing distances between the telescopes. Now, we would love to be able to say we can fill the whole Earth with the telescopes and thus create a virtual dish, an unbroken virtual dish the size of the Earth. But of course, much as we would love that to happen, it's not really practical to fill every inch of the Earth's surface with radio telescopes. So how do we get around that problem that we've got gaps, if you like, between our virtual dishes? Well, I'll tell you about that in just a little while, because there's an ingenious way of solving that. So what VLBI is all about is reconstructing an image. And Mark, what I was going to suggest at the moment, before I get into this, which needs to be done in sort of an unbroken way, would everybody like a break at this point? Would it be a good time to have a break? Because we did start a little late, so would everybody like a break? Well, what's the view?
What do you reckon, Mark? A short break?
If we go to the break and we'll carry on.
Yeah, sure.
10 minutes.
10 minutes is fine by me. Is that? Yeah, it's fine by me.
Okie doke.
Okay, so I make it, well, your time, it's 7:55, yes?
That's correct.
That's correct. So back at 8:05 then? Yep,
that sounds good.
Okay, I'll see you in a bit then.
Lovely. Okay, so I could just remind everybody, this is still going out via YouTube, and that if you do want to chat amongst yourselves, you're more than welcome to, but do be aware that you are going out to the public, and the recording will still be available to them in the future as well.
And may I also say that if there are any questions that you'd like to ask, do put them in the chat window, and we'll deal with them at the end. Okay.
Yeah.
So there we are, and I'll see you back here in 10 minutes then. Lovely.
Been very good so far. I enjoyed this.
I'll give you the tenner later.
We have that in sterling and not euros, please. Right, go and top your cup up.
Okay,
be back in a minute.
It's all gone quiet. Just to let people know as well, after the meeting ends, the Zoom meeting will carry on. We'll end the YouTube stream after the meeting, but the Zoom will carry on if everybody wants to have a chat and catch up and that. And we'll have a talk about the upcoming council meeting as well, and with regards to reopening and getting back into some in-person meetings, which would be nice.
Okay, Andy.
Hello.
Yeah, we were just saying there, when everyone turned the cameras off, it didn't seem to make any difference to the smoothness of the stream.
Well, it was worth trying. So
definitely, yeah. It seems to be based more on what Zoom servers are doing rather than the individual streams, I think. So
okay, well,
but it's good to know.
Yeah, it's always worth trying if you've got a jerky Zoom video. Try turning the cameras off.
Definitely.
You can ask people to turn the cameras back on if they'd like to, by all means. I think that was the last video anyway, so no problem.
Yeah, the sound was great. The sound was very smooth.
Good.
There was no interruptions in it or anything. So
good.
Andy, what was the music with the was it the VLB? You know, where you're doing the 4-minute tour around the different telescopes. Is it I don't know, Jean-Michel Jarre or? Well,
the original music on that video was rubbish, so I put my own music on. It's Tangerine Dream.
Oh, Tangerine Dream.
We may find that we get a copyright strike on YouTube.
It's not happened before with this lecture, so I wouldn't worry too much. So
worst case scenario, we may have to mute that part of the video on the recording.
Okay.
But that's the worst case, and everything's on screen anyway. So
exactly.
It'll only be for those portions. It won't be for the whole video.
Yeah.
It happened with we had Jacqueline Bell. Came to speak for us, and she used a clip from the astronaut program from BBC, and that got, like, the moment the stream ended, we got a notification saying take it down.
The BBC getting switchy.
Yeah.
Well, this has been live on YouTube before, so it was no problem.
Hopefully it'll be okay. Right, okay, we're on 8:05, so we're coming to the end of the break, and hopefully everybody's back with us. Before we carry on with the lecture, I would just like to mention this is the William Lassell Memorial Lecture. We have one of these every year, every October.
Oh, right.
And it's not necessarily always about William Lassell. It's just to remember a very prominent astronomer from the Liverpool area, and we just like to mention that.
It's actually an honoured lecture to be to open with as well. I think we always have an eminent astronomer, so you're in good company. I think, Andy.
I am very honoured. Thank you so much. Thank you for the opportunity.
No problem. Right, okay, it's 8:05, so if we go back into the lecture, I shall mute myself.
Right, okay. Just one final thing, Dave. As I said, that was Tangerine Dream, and I picked the music before really seeing the title. And the title of that track is actually called A Night in Space. So that's quite appropriate.
Quite apt, yeah.
So there we are. Okay, getting back to this then, VLBI, reconstructing an image. Why reconstructing? Because the image of that black hole was not, if you like, a live image. It was a reconstruction of what had been there. And the reasons for this we're going to talk about in a little while. But basically, VLBI is always a reconstruction of an image rather than you seeing something live, if you like. It's a reconstruction. So let's explain exactly how that works. Now, we're going to go on a little walk in the countryside. So you go out in the countryside one fine summer's morning, and you come across a pond. And in the pond, there are some ducks. And you start to ask yourself questions about the ducks. How many ducks are there? What direction are they moving in? How fast are they moving in? Which direction are they moving in? Now, you may say, well, why can't you just look at the pond and answer those questions? And the reason is you can't, because these ducks are the world's most dangerous animals, because they are invisible ducks, and you can't see them. So you're standing there by the pond asking yourself these eternal questions like how many ducks are there in the pond, which direction they're going in, etc. How big are they? So how are you going to work this out? Well, what you can actually do is...
As if by magic. I can create a big crowd of invisible ducks.
Yes, that's Dougal just claiming that he can create a big cloud of invisible ducks. What you can actually do is you can look at the ripples that those ducks are generating in the water, and you can see that something has been in the water, something has caused those ripples, but you can't tell an awful lot about the objects themselves that have caused those ripples. And the information you get is a little bit restricted. And I'll demonstrate what I mean, because if you look at the duck in the background, that duck's ripples are being blocked from reaching you by the duck in the foreground. And therefore, you don't get to see them. So the information you're receiving is really limited. How do we get around this problem? Well, what you do, you say to yourself, I need more data. Where do I get this data from? So what you do, there's you with your pattern of ripples. You get a friend who obviously hasn't got a life to stand a little distance around the pond and to look at the pattern of ripples that they see. And they will see a slightly different pattern of ripples, but they will have a different information set, a different set of information to you. Now, the important thing here is that you can go on adding people around the pond, and each person will have a slightly different set of ripples to look at. And if you compare those ripples between you, you can come up with a much better picture of what's actually in the pond. But the crucial point is that you all have to be observing at exactly the same moment. Because if you're not, those patterns of ripples become quite meaningless. You need to take a snapshot of those ripples at various points around the pond at exactly the same moment in order to build up a picture of the answers to the questions that you had. How many ducks are there? Where are they moving to? How big are they? Etc., etc. The link between you and your friend, if you like, if you can imagine these are radio telescopes being linked, the imaginary line between you is in VLBI terms called the baseline. And if we have 3 people, therefore we have 3 baselines. Let's add in another person on the other side of the pond, and you can see there that we've increased the number of baselines so that we now have 1, 2, 3, 4, 6 baselines with 3 people. And this is how VLBI actually works, by joining these telescopes together to build up a picture of what was in the pond at a particular moment. In other words, applied to the M87 black hole, each one is receiving slightly different signals from the black hole, and we can compare those signals to work out what was actually there. And this is VLBI. It's quite a simple concept. The maths behind this, as you might imagine, is absolutely horrendous. And while I was putting this presentation together, I did get in touch with a few people to explain exactly how these telescopes are linked and what that's all about, but nobody would give me a straight answer, or I couldn't find one anyway. So this is VLBI. It's a reconstruction of what was at the black hole at a particular moment in time. And in fact, it was lots of moments, because the observing run that acquired all the data necessary to reconstruct the image of the black hole took place, if I remember correctly, over about 17 hours. So it was 17 hours worth of observations spread over several days. Now, let's get back to this question of how do we fill in the gaps between our virtual dishes on planet Earth? And let's explain this. So on the left-hand side, you've got 3 radio telescopes, South Pole Telescope, the one in Europe, and so on in France, and they are linked with their baselines. Look at the right-hand window, and this is the image that they've reconstructed. But as we know, we can't fill the Earth with radio telescopes, so how do we get around it? We use a very useful feature of the Earth. It rotates. And as it rotates, the baselines change and fill in the gaps. And if you look at the middle window, as I run this animation, you will see this happening. So there's the Earth rotating, different radio telescopes coming into view from the point of view of the black hole. and the baselines change. And if you look at the middle window, you can see the gaps are gradually being filled in. And by doing this over a long period, we can indeed create a virtual dish the size of the Earth that isn't missing any data. And as you can see on the right, as we add in more baselines, the resolution of the image improves. Now, just to go through that in a slightly simpler way, so we have, let's say we have a radio telescope at the North Pole and one at the South Pole. They're linked with a baseline. And as we know, that creates a virtual dish that size. Now, we set our data recorder running, recording the data from the black hole, and then the Earth rotates. So we get a slightly different baseline, a slightly different view of the data. And that creates a virtual dish like that. And the Earth rotates again, and we get that. So if we do this with all the telescopes in the array, while the Earth rotates, we can build up a virtual dish, which is the size of the Earth. And this is how it was done. It's very clever stuff. These people are complete geniuses. So that's how VLBI works. Hope that's fairly clear. It's not an easy subject if you've never come across anything like this before. However, that's VLBI. The important thing, as we said, was that all the telescopes observe at the same moment. And when we gather all the data together to process it, we need to combine the signals that were received at the same moment. And to do that, there's only one clock that is accurate enough to do that, and that's an atomic clock. Why do we need this? Because as you can see, the radio waves arrive from the black hole at a slightly different time at each telescope site. So these individual signals need to be synchronized or correlated, if you like, so that we are looking at the same signal arriving at exactly the same moment. And as I said earlier, this is why VLBI is a reconstruction of an image, because we need to reconstruct what the telescope saw at a particular moment, because the waves arrive at that radio telescope at a slightly different time to the others. This is data, this is information traveling at the speed of light, but it still takes time to get from one telescope to the next. So at each site in the Event Horizon Telescope array, at each radio telescope, they had to install atomic clocks, which would timestamp each individual radio wave down to accuracy of a few squillionths of a second. And here's the team that have just finished installing the atomic clock, which is a type of atomic clock known as a hydrogen maser, at the Alma telescope. And this team had to go around all of the telescopes all around the world in the array, installing a similar atomic clock so that the signals could be timestamped and synchronized. And what you end up with is this. You've got several radio telescopes here. I've put in 5 here, and they're all receiving the same signal, but at a slightly different time. And to bring all these together and correlate them, not surprisingly, we need a very, very powerful computer. And that is a type of supercomputer called, believe it or not, the correlator, because it correlates the data. And we bring all those signals together into the correlator, and what comes out is one signal, which is the combination of the data received at all of the radio telescopes. And this signal can then be used to generate the final image. The correlator had to synchronize each of those data streams to the accuracy of a millionth of a second. That's the accuracy that was required. So, as I said, only an atomic clock would provide that level of accuracy. The correlator processed 10 times more data than an average observing run at the LHC in Switzerland, so the Large Hadron Collider. So it was an incredible amount of data, roughly 5.5 petabytes of data, which had to be synchronized. And guess what? Even with a supercomputer like this correlator, it took a long time. And this is why we had to wait nearly 2 years for the image after the data had been acquired in 2017. A lot of that was the simple processing time of 5.5 petabytes of data that have been acquired from the radio telescopes in the array. There were all sorts of problems that had to be overcome. First of all, the exact location of each antenna in the EHT array had to be known to millimeter accuracy, because with VLBI, you need to know exactly where the telescope is. You need to know exactly how long the baseline is, otherwise the thing doesn't work. Now, when we talk about the location of each antenna, you may say which bit of the antenna needs to be known to millimeter accuracy. Well, I found a rather poor diagram which will demonstrate this. It's actually the focal point of the radio waves on the dish. So the radio waves hit the parabolic antenna, get bounced to a receiver in the middle of the dish, and it's focused at a particular point, and it's that point that has to be known to millimeter accuracy. So again, incredible engineering going on here. As we said, atomic clocks had to be installed at each telescope in the array. And there was another problem at high altitudes. For example, up at the Alma telescope, high on the plains of Chile, your PC is cooled with a fan. And at high altitudes, there isn't enough air density to cool the computer. So they had to develop a cooling system for the computers that didn't depend on fans. And that's something that they did. So another amazing engineering feat. I'm not sure exactly what they did, but they didn't need fans to keep the computers cooling. Temperature variations at each site can deform the telescope, which changes the length of the baseline. And that's another problem they had to contend with. The difference in temperatures can change the focal point of each telescope, with the metal in the dish flexing and so forth. So that they had to deal with temperature variations. They had to build that into the equations. They had to know the differences in temperature between the dishes of those telescopes. The South Pole telescope had an additional problem. It's on ice, and the ice keeps moving. So therefore, again, the length of the baseline keeps changing, and that had to be known to high accuracy, the exact speed of the movement of the ice, in order to build that into the equations to, if you like, cancel that movement out. The weather had to be good at all observing locations. Well, you can say, hang on a minute, with radio astronomy, the weather doesn't matter. Well, unfortunately, when you're dealing with VLBI, it does. Because when you get a low pressure area, the refractive index of the atmosphere changes, which messes with the signals. It's okay with one radio telescope. It doesn't matter. But with multiple radio telescopes, it does matter. So they had to wait until there was good weather at all of the observing sites around the world. And they had a run of 5 days of good weather. 4 out of the 5 ended up with usable data. So in the future, one thing that will place a restraint on when they can observe is simply the fact that they need good weather at all telescopes in the array. And, that doesn't happen that often. So they were very lucky in the spring of 2017 to get 5 days of good weather. There was no money to buy backup hard disks to store the data on. So it was really, a wing and a prayer sort of thing. If they'd had any hard disk failures, they would have had enormous problems, because they certainly didn't have any money to buy a second set of hard disks. So the data was stored on hard disks, and those hard disks had to be then flown to the data centers in Massachusetts and in Germany. And you may say, well, why didn't they just send the data over the internet? I suppose you haven't ever tried sending 5.5 petabytes of data over the internet. It's not up to it. It really isn't up to it. I tried uploading a terabyte of data recently, and it just gave up after about half a terabyte. So the connection failed. So the internet, the public internet, is not built for high speed, high volume data transfer. And there was simply too much data to send across the internet. Also, the moon's gravity deforms the Earth crust. It pulls it up and down by a difference, I think, of about 9 feet. So the altitude of the telescopes was changing as the moon passed, and that had to be built into the equations as well. And that's not something we can do anything about, of course, but that was something else, the effect of that to cancel out of the data. The software that they used to build the image had to filter out gas in the Earth's atmosphere, gas between us and M87, and any gas in the vicinity of the black hole that actually wasn't part of the black hole, just sort of random gas. So they had to write software that would filter out all of that as well, which was very, very difficult because that gas obviously was emitting radio waves. So they actually had to, cancel out all the extraneous radio waves from the gas between us and M87. And they also had another problem because the way that it was organized was that the data was given to 4 different teams of people to analyze. Now, the people behind the Event Horizon Telescope knew that there's this thing called cognitive bias, that people are very fond of seeing what they want to see. What they didn't want was for people to build an image of the black hole that they thought should be there. Because we all know what a black hole, we've all seen pictures of what black holes supposedly look like. And they didn't want to introduce that into the analysis, people coming up with images that they thought should have been there. Cognitive bias is very strong with humans. For example, is this a chihuahua or a muffin? Dog or mop? Sloth or pain au chocolat? You see, you can look at pictures and see things that you want to see or you think are there rather than what actually is there. And that was a very, very dangerous thing as far as the data was concerned, that people would introduce things into the data that they unconsciously they thought should have been there. And the way that they did that was to make sure that of the 4 teams, nobody knew who was in the other teams, so that they wouldn't be influenced by them. They wouldn't talk to each other, and they would come up with just their own ideas. And then you can say, if all 4 teams came up with the same thing, you can sort of more or less rule out cognitive bias that's caused by that. You'll never rule it out entirely, of course, but they went to great lengths to make sure that this effect of cognitive bias was minimized. The hard disks filled up 6 cubic meters. That's how many hard disks there were. 5.5 petabytes of data, as I said. And the hard disks were filled with helium. The reason for that is that helium is less dense than air. If you fill hard disks with helium, because of there's less air resistance, the read-write heads can move faster. So helium-filled hard disks are much faster than air-filled hard disks. And obviously they wanted the fastest hard disks going. And there's Dr. Katie Bowman, who was in the media a lot at the time. She became associated with the Event Horizon Telescope. And there she is with just some of the hard disks. And Katie Bowman was the person who wrote the software algorithms to cancel out radio emissions from gas in the Earth's atmosphere. And she did an amazing job. Without her, that image would have been greatly degraded in quality. Unfortunately, she was a woman, and people went mad on social media. She came under the most vicious attacks on social media simply because she was a woman doing what many people thought was a man's job. And she was really personally attacked for having the temerity to do something marvelous like this, being a woman. And it was disgraceful, absolutely disgraceful. I don't know how she survived that because, there were some real idiots out there claiming she wasn't a real scientist, saying she hadn't got any qualifications and the work had really been done by men. She was incapable of doing the work, all this sort of stuff. It was just terrible. Social media's got a lot to answer for, in my opinion. But there we are. So there's Katie Bowman with just some of the hard disks, looking very happy. So we have 7, starting from the top here, we have 7 radio telescopes. Then there was another problem. When the observing run ended, the South Pole went into its winter. So they had to wait until a plane could get into the South Pole many months later to collect the hard disks. So that was also what held up the processing. They had to wait for the hard disks to be collected from the South Pole telescope. They were then processed at the 2 processing centers and given to the 4 imaging teams. Just out of interest, in case you're into this sort of stuff, processing teams 3 and 4 used a software method called Clean, and the other team used something called RML. Now, I have no idea what they do either, but just in case you're into that. 2 different types of analysis. But they came up with these 4 images from the 4 teams. And I've put Katie Bowman's picture in there because that was the image from her team. But the other images, as you can see from the other teams, are very similar. And on July the 24th, 2019, the 4 teams got together to have their first imaging workshop to look at each other's work. And they were all amazed that they'd all managed to come up with something that was fairly similar to each other's work. They all, look at that, they all got the Doppler beaming in the lower half of the disk, as you can see. So we can say that was definitely there. That's not an artifact just introduced by 1 or 2 teams. They all saw the Doppler beaming, which was great. And well, they were just amazing images, absolutely amazing. So what they did with these, they took the best 3 of those images and they combined them into one image, which was the final image. And that is what we ended up with. So what has been happening since then in terms of the Event Horizon Telescope? Well, a couple of months ago, there was an amazing discovery that the light coming from that disk of material around the black hole is polarized. And this is an effect of the black hole's magnetic field. And this is pointing to the magnetic field lines around the black hole. So scientists have actually learned a lot about the magnetic field around the black hole by studying that polarized light. They didn't realize before that the light was actually polarized, and then they just discovered it by accident. And that is telling us a lot about the magnetic field around the black hole. Also in the news recently, another galaxy, Centaurus A. And here is a composite image in X-ray optical and infrared of that galaxy. As you can see, it's got 2 jets. Well, one is more visible than the other in this image, but there are 2 jets at angles coming away from this black hole, like the one in M87. And using the Event Horizon Telescope, they got a close-up. And this is it. The image on the left was the best image up until then of the jets. And look at what the Event Horizon Telescope found. An amazingly high-res image, getting in a lot closer. And the resolution of that image on the right, it's picking out features that are less than half a light day across. So very high resolution from that distance. Can't remember how far away Centaurus A is. Perhaps somebody knows. It's a long way away, obviously. And there's an arrow pointing to the location of the black hole, which we can't see, of course, because it's invisible. But you look at the difference that the Event Horizon Telescope has made between the previously highest resolution image on the left and now this new image on the right. This is what the Event Horizon Telescope is capable of. And in its current observing run, which has now, I think, got an extra 4 telescopes in the array, the results from that should be absolutely stunning. This image, by the way, was acquired at the same time as the M87 black hole image in 2017, and it took a long time to process, which is why we've just seen it. And this came out, I think, about a month ago or 6 weeks ago. Amazing image of the jets of Centaurus A. Funnily enough, what they've managed to glean from this is that the jets may be hollow. And we don't quite understand why that is. They're not solid jets. They're sort of cylinders, if you like, empty cylinders, if you want to look at it like that. Also, that could also be caused by the jets rotating at high speed. And we don't really know at the moment which one of those it really is. But, there's a lot more work to come on this yet. So in a nutshell, the EHT, Event Horizon Telescope, has been given $19 million by the National Science Foundation in America to develop the next generation EHT. They want to put a lot more telescopes in the array, including some in space eventually, which will give us very long baselines and therefore, much higher resolution. And high resolutions, less processing time, because now they've got the basic algorithms. It shouldn't take as long in the future to process the images. And the goal is to produce videos of activity around a black hole, perhaps over the course of hours. So that would be absolutely mind-blowing to see a black hole change over hours. So that's the future for the Event Horizon Telescope. And that's it, guys. So a good future. We've got a great, bright future, an amazing future for the Event Horizon Telescope. It's going to uncover things that we probably couldn't have dreamed of. So for now, thank you for your attention. And if we have any questions, I'll be happy to answer them. I've got a really loud cat meowing by my feet at the moment. So let me just throw the cat out. Come on then.
So I've got noted a couple of questions that we've had.
Right.
Would people like to read their own questions out, or would you prefer me to read them out? I think first of all, we've got Colin. So
do you want to read them out, Mark?
I'll read them out.
Yeah.
Then. Okay. So from Colin Murray, are there any other black holes you plan to image? Even if image is the wrong word, but go with them on it.
No, image is fine. Photograph is wrong, but image is fine. Right. So in the same 2017 observing run, they imaged the black hole, the supermassive black hole at the center of our galaxy, Sagittarius A star. We haven't seen that image yet. They're having enormous problems with it because we're so close to our black hole, astronomically speaking, a mere 26,000 light years. There's a lot of activity around our black hole. There's a lot of gas, stars going around it, all sorts of radiation differences. And they're finding it very difficult to get, if you like, a still image of that black hole because of all the movement around it. It's like trying to take a photograph of a moving car. It's a moving target. Excuse me 1 second. So they say that they plan to release that image before the end of this year, if all goes well. But it's taken a lot more processing time to cancel out the effects of all of the material moving around the black hole. Other than that, they want to do the Andromeda Galaxy as well, M31, because that's a inverted commas nearby galaxy. So yes, I mean, the sky's the limit. You've seen what they've done with Centaurus A. And we can expect more of the same, basically.
Is there pressure on them to image, in particular, something like Andromeda, because it's a well-known object that everybody knows what it looks like visibly? Are they under pressure to get some pretty images of
No,
that,
not really. There's no pressure. As always, these things are decided committee. They look at the science case by case and work out what the best target is. But there's certainly no pressure, which is good, because the last thing you need with that sort of work is pressure.
Yeah.
So
a lot of the time it comes down to funding, doesn't it?
Yes, of course it does. That's right. That's right. So the scientists involved with the project are making the decisions about what the best targets are, and it's not necessarily a case of what will make pretty pictures. It's what will deliver the best science.
Yeah. That's excellent. Okay. The next question is Dave Galvin. Am I correct in thinking that we are recording the magnetic field of the black hole?
We're not recording it because we're only receiving radio waves. So, but thanks to that image of the polarized light, we can work out where the magnetic field is and what its structure is and things like this. But we're not recording the magnetic field directly because the telescopes only receive radio waves.
Yeah. Are those radio waves, so are they given off by, like you get with, I'm trying to think of the right term, when you have electrons flying around the field lines.
Yeah, that's right. Because
is that what we're seeing, or
yes, what we're seeing? You're referring to synchrotron radiation,
yes.
which
Couldn't
is
remember the name.
Yeah, which is electrons spiraling in a magnetic field. Yes, because of the magnetic field, that material around the black hole is highly ionized, and that's what we're seeing the radio waves from. It's blatting out radiation across the spectrum, because it just is. It generates radio waves. If the material is hot enough, which is not the case with this one, you get X-rays as well, because anything really hot radiates X-rays. So it's just the case that these radio waves are coming from the material around the black hole as the electrons spiral through the magnetic field.
Okay. I've had a question myself. In the Doppler beaming images, the 4 images from the different teams, why was the Doppler beaming in slightly different positions for teams 2, 3, and 4? 1 and 2 seem to have them aligned, and then 2, 3, and 4, they were all slightly different. Is it a case of just the image was rotated slightly? Could be.
I don't actually know, Mark. I think you'd have to ask the teams why that was. But the important thing was they all got the Doppler beaming. That was definitely the crucial bit. Yeah.
That's my question done. Anybody else got any other questions?
No.
Everyone's very quiet. Are they all still there?
Yeah. Can you hear me, Mother?
We can hear you. We can hear you, son. It's okay.
Okay. If nobody else has any questions, then I'd like to pass over to Dave Galvin to give the vote of thanks.
Thank you, Mark. Yeah, I can only say that you've covered every aspect, I think, Andy, and as always, you do it in your unique way, I think. A fascinating talk describing how to image a black hole or to record a black hole. You've used the fly doing sit-ups, invisible ducks. I do not know any other lecture on black holes that I've ever used an actual video of a fly doing a push-up.
Isn't it great that somebody created it? So somebody actually wanted to illustrate how much an erg is. I think it's brilliant. So,
it's fantastic. You talk about the use of the very long baseline interferometry, and it's you think, well, okay, I remember the Merlin project, and that's what it reminds me of course.
Yeah, of course.
And you forget you've got to take into account that the Earth is rotating as well. And you mentioned about the moon affecting. The actual elevation, it rises several feet, but but that improves the resolution then, because using the rotation of the Earth to bring that radio telescope into the field and improve the signal. Absolutely amazing.
Absolutely amazing. And actually, I just want to say that as regards to the video of that fly, I thought there's never going to be a video of a fly doing a push-up. No, there can't be. Oh, yes, there is. It's the only one, though. It's the only one on the whole internet.
The power of the internet. And no flies were hurt during the
No, that's right.
Of course.
That's right.
Yeah. I just want to thank Andy for excellent presentation. Unique presentations, as always. A question was asked about the graphics. A comment was made how excellent the graphics are, and we talked about this the other evening. You do your own graphics as well.
Yes, obviously not the videos, but I do everything else myself. Yeah.
It really puts the points across. I think I really enjoy them. I'd like to ask all our members if you would virtually, give Andy that welcome that we always do, and a thank you. Obviously, it's virtual, so we unmute our mics and our cameras and applaud, and hopefully across the distance to Spain, which is not that far. And
900 miles.
Rotating, of course.
900 miles, give or take.
We thank you, Andy. Thank you very much.
My pleasure. It's been great. Thank you for having me, and thank you for inviting me to do this special lecture. So I'm very honoured.
Thank you so much.
Thank you. Thank you very much.
It's been a really good talk.
You've been a wonderful audience. I've had a great evening. This wasn't it. Sorry.
Maybe the next one.
So there we are.
What is it? LIGO next, maybe. We'll see.
Yeah, why not? Why not? I'd love to come back and tell you all about LIGO.
Excellent.
And so and there's lots of recent news about LIGO that's quite exciting. So so there we are. All right then, guys. Well, I'm going to love you and leave you.
Okay, Andy, and I'll
okay.
see you probably tomorrow evening.
If
you're available. Oh, sorry, no, Monday. Yeah, I
Monday.
just come back from sunny Llandudno, so I've lost track of the day.
I guess what's is happening on Monday, yeah?
Monday, yes.
Yeah, okay, great.
All
right then, guys. Take care of yourselves. Stay safe, everybody. And,
Thank you, Andy.
And I will see you soon.
Take care.
Bye. Bye.
Bye. God to your daughter as well. Don't
Thank you very much. Yeah, I've already had a little go at her about changing my name, and of course I got the predictable. Wasn't me.
Wasn't me. No.
Must have been the cat. Yeah.
Cat.
Right.
The cat's
Take care,
a fan
guys.
of anime.
Take care, Andy. See you
Bye.
soon.
Good night,
Bye.
Andy. Okay, right. So I'll move on to item 10 of the agenda, the date of the next meeting, which is going to be Friday, the 19th of November at 7 p.m. And of course, we'll be back on GMT by then. And our speaker for next month is going to be Dr. Steve Barrett again, and he's joining us with part 3 of his Fiat Lux series of talks. If you want to see parts 1 and 2, they're both on our YouTube channel. There's recordings there for you. And part 3 is just a continuation of that. It's currently the last in that series, although there may be more in the future. Right, okay. And I will bring the meeting to a close then. It is 8:44 p.m. And I'd like to thank you all. And with that, I will stop the recording and stop the YouTube stream. So if you bear with me 1 second while I do that.